Alright, so hello and welcome. We're back for another problem. Hopefully this one's not too quick. I kind of should go to bed now, I think. Excuse me, I just want to get a little bit of time in here and work on something. I really could have and should have spent a little more time today. Yeah, days just kind of roll one into another, I guess. I'm also like not using my time as efficiently as I could or should. I kind of need to be like a little more focused. I like to take breaks. I get really distracted. It's not ideal. But yeah, so here we are. Order of largest plus sign. Let's see. It's a marathon, not a race, though. But even still, I still gotta run. Order of largest plus sign. You're given an integer n. You may have an n by n. You have an n by n binary grid with all values initially ones, except for some indices given in the array mines. The ith element of the array mines is defined as mines of I equals x sub I, y sub I, where grid of x sub I, y sub I is 0. Okay. Oh, I see. That's a little bit confusing. Oh, I think I understand. Okay. So you get them. Okay. So the mines will. All right. I think I get it. Turn the order of the largest axis-aligned plus sign of ones contained in the grid. If there is none, return 0. Axis-aligned plus sign of ones of order k has some center. Grid RC row column equals 1, along with 4 arms of length k minus 1 going up, down, left, and right, and made of ones. Note that there could be zeros or ones. Beyond the arms of the plus sign, only the relevant area of the plus sign is checked for ones. Okay, got it. So the minimum side is what we're looking at, minimum length. So if you couldn't go beyond 1 on the left side, then it would stop there on all sides. Okay. So n equals 5, mines, there's 1 mine here, 4, 2, and in the above grid the largest plus sign can only be order 2, one of them is shown below. The order actually includes the middle element, I guess you'd say. So one line, one arm, I guess they call it 4 arms, so 1 arm would be k minus 1, and then k would be obviously add 1 for the middle portion. So this is of order 2. Okay, and I think the best you can do is 2. So this is an interesting question. No plus sign, return 0. So if there are no ones at all, then return 0. N is between 1 and 500. The number of mines, we're going to have 5,000. So it could be 2,500 and 5,000 mines. All the pairs, x sub I, y sub I are unique. All the mines are unique. Okay, this is an interesting question. So how are we doing on time? Get 3 minutes, or we're 3 minutes in. So this problem is interesting. I'll go explain in a moment. I actually don't have thoughts on this. I should take that back. Won't be explaining much of anything because I don't know how to solve this, or at least not immediately. I could brute force this, certainly, where you would loop left to right and try to. What you could do in theory is take each row column position, so there's O of n squared, we'll say, of these positions, and try to sort of iterate outwards the largest plus sign from there. And if you did that, then you could, in theory, find the largest plus sign, and that would be O of n squared times k, I suppose. Now the problem with that though is that k could be n over 2, I want to say. Or it's really O of n squared. Yeah, O of n squared times k, I guess is fine. O of n squared k. But k could be proportional to n, so you have O of n cubed in that case, which I think is too expensive. I mean, it's not too bad, actually, 500 cubed. This might be actually really the only reasonable way to do this. 120 to 25 million so maybe a little too expensive. I think you could do 100 million and you'll still pass. Your like 100 cubed usually is fine. No, excuse me. Yeah, no, I think 100 million passes. 100 million passes LeetCode problems. I think it's like 100,000. Basically, like 100,000 usually is like 10 milliseconds. So then if you multiply by 1,000, that gives you 10 times 1,000 milliseconds, which a millisecond is. Oh, actually, that might be too expensive. Yeah, I'm wrong about that. Actually, might be too slow. I don't know. I don't actually know. I know O of n squared log n on 1,000. So you do 1,000 times 1,000 times log n, which is yeah, there you go, 10 million. This is like 80 milliseconds or so, or 100 milliseconds. So times 10. Yeah, so I think about 100 million you can do and still pass. So I think we can actually do the cubic algorithm. O of n's, you basically, yeah, I still say it's cubic. I think it's fair to say it's cubic. And obviously you just dump the mines into a hash set, so that way, excuse me, dump the mines into a hash set, and so you can quickly check, you know, when you're sort of growing your what do you call that? Growing each cross, we'll call it. I think there is a simpler way to do this though, and I want to say it's like, I think there is a more efficient way. I really should just go to sleep. I don't know why I'm doing this. Why I decided to wait so long to do this. I guess the more efficient way would be, you need to fit your cross between each mine and either each other mine or each boundary. And so that's one thing, is that there's sort of like you can sort of find out what the longest stretch possible in the first place, or horizontal, vertical, and horizontal. Oh boy, did I keep touching my face and getting? Oh no! Touch my face and it causes it's not injury, but it's like I get yeah, I guess injury is right. Yeah, I get sort of bacteria on my face, and then I get some kind of acne or something. It's basically acne, a form of acne. What I was trying to say is, yeah, you can maybe find the largest length, either horizontal or vertical, between the mines and the array, and you can do, I guess, for each row and each column, you can find the largest vertical or horizontal stretch, and then basically, well, the tricky thing is that you're not just looking for the longest stretch, you're also looking for I guess what I want to say is maybe we can find at each row and column pair, we can find the longest stretch in the vertical and horizontal distance for every row and column, and we can do that in row, row column time. And if you do that, not row column time, but m by n time, O of m by n time, where the matrix is m by n. And then if you do that, then you can just take the largest, you take the minimum of that row and column, the vertical and horizontal values, and yeah, those vertical and horizontal values, take the minimum, and then obviously k is going to be, I think you take that minimum and you'd say, if it's, I think you subtract 1 and divide by 2. Yeah. Subtract 1 and divide by 2. And it's integer division, so if you have 6, then the best you can do is put a 5 in there. So that would give you k is 3. Subtract 1, divide by 2. K is 2. Excuse me. You subtract 1 for the middle element, and then you split the remaining values into 2 categories, and you use integer division to lop off the half portions, I guess, something like that. Actually, the exact, I guess, algebra for that is a little bit confusing, but yeah, I think subtract 1 divided by 2 is correct. And then and take the floor, and then yeah, that would give you k minus 1. So for instance, 6, you would get really would be of order 3. So then k would be 3. So then actually you add 1, subtract 1, divide by 2, and then add 1, which is a little bit confusing, but yeah, integer division. That's what the valued return, and you just return the maximum of all of those values and all of the spots in the array. Now the thing that's tricky about that is basically you would associate you could do this in quadratic time. You can do this in quadratic time proportional to the size of the grid. The thing that's tricky about this is that you would need to, or one approach is that you would need to basically, for each sort of stretch of, I guess, open grid cells between either an edge or a mine or between mines, either in the vertical or horizontal direction. I guess you do row by row and then do column by column, do them one at a time. You would associate, I guess you can write 2 different matrices instead of, we don't need to use hash sets, we could use 2 different matrices that we write to that would store the I guess the maximum height and yeah, so I don't know how I would do this without using memory more efficiently. The problem that I would run into is I would want to collect, I would do these in 2 different phases. One phase you basically assign the sort of associated longest stretch of horizontal grids and then longest stretch of vertical grids. Or yeah, horizontal and then vertical, right? Vertical is this way, horizontal this way, between the mines. And then run another routine where you would actually calculate at each row column point what the cross in the intersection, the what value for k we can use. So we take the minimum of those two values, and then check that against the current maximum that we have. So I have an idea for this. I think it's definitely quadratic time, but it uses quadratic memory, which is not too bad given that this is the. Actually, no, the mindset is not actually quadratic memory. So it's so it is actually quadratic extra memory, which is interesting. I'm kind of wondering if there's a way to save on that. I don't think so, because you kind of need. You would need to. I mean, you can do things somewhat recursively, where, like, if you did all of the first row, you have all of these. The first stretch you go through, you say, okay, we found out what one of the values are for the stretch. Now, for each of those, what you do for each of those rows, you then need to find out what the horizontal values are, right? And you could do them one by one, and you wouldn't use memory doing that, but the problem is that you need to remember the vertical part for each of the horizontal parts, and then you would be done with the vertical portion, but then each horizontal portion, then you have another sort of vertical part that's queued up to process. And you would need to remember, like, the vertical part, so it would kind of switch between the vertical part to the horizontal part, and then that horizontal part, there's the other horizontal parts that you have to keep track of those values, and now perform the vertical portions on each of the vertical parts of your horizontal portion that you just processed the first one. And then you have to also update each of the cells for the vertical parts, or excuse me, horizontal parts that you're now sort of moving through as well. So it gets a little bit confusing. I think it's a little bit too hard to try to keep track of, like, what things you've already processed without using some memory. I think ultimately you'll end up using some memory anyway. So yeah, so let's try that. We're gonna have something like this. We'll have, so we'll say vertical and horizontal. And this is going to be n, and these will also be vectors of size n. And I think there will be integers. There will be integers. Start off at 0, all of them. Okay. So process vertical stretch for each row, column, pair, row, and we're going to say process each column. So we'll start with, so it's actually going to be each column, we're going to move row by row and process. Now what we're going to do is we're just going to go straight down. So we'll say you could start from the top. How are we doing on time, by the way? 20 minutes. Okay, it's probably take me another 20 minutes to finish this, I think. Starting from the top row, we can have so what's going to happen is it's actually going to traverse each row sort of quote unquote twice. So we're going to have int, so we're going to have a right row, just 0. And we're going to say, okay, from the top row, we'll say if, say int x equals, not mines, yeah, mines, if, we'd say if mines of, oh, actually, place all of the mines into a hash set, or into, yeah, hash set, unordered set, so that we can easily determine given position, say mine, contains a mine. So we can do standard unordered ordered set of, we're going to say standard vector int of, yeah, so it's just unordered set, and we're going to say mine position, or just mine set, we'll say. And one thing we need to define here is so this is kind of a tricky thing, but we have in unordered sets, we have a hash, okay, and the hash itself is, excuse me, enabled or disabled, tainted, untainted, or poisoned. Interesting. Well, basically, could define our own hash. Yeah. This is what we want. Standalone function object. Yeah, so we're gonna say custom hash. We'll do it that way. Well, I prefer that to custom hash. Size t operator s const s, which is, it's gonna be, in our case, standard vector. Oh. We want, can actually convert these to tuple. Well, we really don't need to do that, I think. These are integers. Do we need size t? I don't think so. Yeah, okay. Oh yeah, the hashes are, yeah, actually the hash, yeah, I take that back, yeah. Okay, that's fine. It's interesting also how this works. It's kind of neat. You generate a hash object, it's just which is functional, and then call it. So do that on x1, x0, h1, h2, and then hash boost, yeah, boost combine. We just XOR with one of these bits shifted, and that's our custom hash. Super simple thing. Also with const no accept, we use that as well. Sure. And so this can be custom hash. And we actually want to then place the mines.begin, mines.end, which I kind of dislike. We could do like type def, custom set. Yeah, I tend not to memorize this struct, but maybe I should. And now, what we're going to want to do is now we can check. Count. So we can say if mindset.count of we would say we actually can use vector int test, which is really really row column. So this, I kind of question this. I think this is okay, but it's a little bit awkward. We can say you could use maybe a key. You could do it this way. It's maybe better. So I don't have to generate this every time. There we go. So whether or not this is a mine, you can also have another routine. If row is greater than or equal to n, or we reach a mine, and then what we're going to say is right row, then update the vertical. We'll say vertical. We'll say update the values in the given row with the I'll have a count as well. Increment the count. So we'll say update the values in the given row with the count represents the longest vertical stretch. Contains each of these cells, grid cells. Yeah. Update the values in the given row or given column with a count which represents the longest vertical stretch. So actually we'll call it stretch. That's better. So if we see a mine, then we're going to say so the right row, we're going to say int x equals right row. Yeah, right row. X is less than the current row. We're going to increment x. So we don't write to the mine itself. And we're going to write vertical of the row and the column is going to be equal to stretch. Reset the stretch. The next stretch computation. Update the right row. The next update for the next iteration. So right row is now going to move past row. It's going to go to row plus 1. And we're also going to increment the row. Excuse me. Well, actually here, we would see the mine. Yeah. So we would see the mine, and then we're going to go to the next. So right row is going to go to the next spot. Now, if the next spot is also mine, we actually need to be careful because the right row can be put onto another. Oh, you know what? I made a mistake. Oh no. I did something wrong. There was actually, I had a question that was similar to this one that I made a mistake on. Oh no. I thought I did so well. I forgot. Shoot. Oh no. I was supposed to use a loop, just like in this one, in this question. Same problem that I hit here is the same problem that I hit in the loop. Oh no. I made a mistake. I made a mistake. What could happen is that you could have a no. Oh, I made a mistake. No. There was actually a question with a subtle edge case that I forgot about. Oh, it's very subtle. Oh no. I made a big mistake. Actually, hold on, I gotta think about this for a second. I think the, no. See, this question is different. So, I was actually okay. I'm fine. I had a very similar problem in an interview not too long ago, and I just realized I may have actually incorrectly solved that other problem, but that other problem is kind of special. It was a little bit different how it was set up, so I don't have the same problem I'm going to have here. Here, what can happen is you don't have, in other words, your right row comes after it gets set up to the next mine, but it's possible that so actually what you would need to do is two things. You want to progress the row position, the row pointer, I guess the row position, progress that past all of the mines, because there could be multiple mines lined up in the column. And I was just thinking, oh man, I didn't actually run into the same problem. I thought I almost did. I almost ran into a similar problem. The other problem that I was working on, I had actually considered this. So, no, it's okay. All right. I was like, wait, I think I did something wrong in my interview. No, you're fine. You're fine. So anyway, so we're gonna update for the next iteration. We'll say while row is less than n, and so while row is less than n, and mine set dot count of row so what's interesting here is that we're going to increment, once we exit this loop, we're going to increment the row past this first mine, but there could be more mines ahead. So we'll do row plus 1 if the next ensure that we skip consecutive mines. So this is just going to skip a consecutive mines. Now, what can happen is, right, so we're going to check, we haven't jumped to the next spot yet. We're going to, but if those are mines, then we're actually going to keep going. And we're going to keep going. So we could say key of 0 equals row plus 1. And oops. We're going to say key. Now what's interesting is, and we'll say, well, while row plus 1 is less than n, how does this handle the end at the bottom if we go off the edge? So yeah, we update our stretch. We set our right row to really just to, I guess, to row plus 1. So yeah, it should be row plus 1. So let's say we have like 3 mines, consecutive mines. We have the first mine. Our row is then going to, we're going to write through our right row down to that spot that we're at that's a mine and not touching the spot that's a mine. And then we're going to update our key to the next spot and then check if, and each time we're going to update our key to the row, really row plus 1. Yeah, that's confusing. But we're going to see there's row plus 1 as long as we're not off the edge. We'll come to that in a moment, but we're going to say set our key to row plus 1 and check if that's a mine. And if it is a mine, then we're going to increment row past this first mine to that mine. And we're going to keep going until we're at the last mine. So row is pointed to that last mine. And then after this iteration finishes, row will be then past that mine. Now, if we go all the way down to the bottom of n, the number of rows, I guess, what we want to do is say we're going to keep the row just before n, right? Row plus 1 less than n. And if there's a mine, so it could be a mine at the bottom, there's going to be the two spots. So we're actually not going to go past all the way to the bottom. We're going to say that a mine at the bottom, if that's a mine, then we're going to update the row to the very last row, and we're updating this key, but this will exit, so it doesn't matter what the key is here. And we'll be at the very last spot, very bottom. Excuse me, if row plus 1 is a mine, so it's not, yeah, it's interesting because if row plus 1 is equal to n, so if row plus 1 is less than n, which means we're not going to the very last row, we're going to the second to last row. That's what row is going to be equal to. So row could be equal to the second to last row. Is that right? N minus 1 is the last row. N minus, yeah, oh, that's so confusing. But yeah, the row could be second. If there's a mine there, then we're going to update row past that. Actually, that's going to go past again. So that's kind of weird. Doesn't seem right. Why? How are we trying to do this? We're looking ahead one row before we update past the row we already looked at. Oh no. So row plus 1. We're only, yeah, okay, excuse me. So right, if the second to last is a mine, then row is actually just before that. We update row to that spot, and then we stop there, right? So we're on this mine, and then we're going to jump ahead row one more time, But what's going to happen is the last spot there, that could be an open spot or a mine. And we want to set the right row to that spot. But I think the thing is that I should really, actually this doesn't matter. If we can write to the vertical portion, we can write 0 stretch. I'm sorry, we shouldn't actually do this part. We can skip this altogether. It's fine to write 0 things here. Yeah, I'm making this more complicated than it needs to be. So the right row is going to be row plus 1, which is going to go past the mine. And then if we see another mine, then stretch is going to be 0 again, and we just write to that spot 0, and then push right row ahead, and we don't actually need to skip the consecutive mines. That's actually fine. We can just write 0 to this vertical. Okay, I'm making this more complicated than it needs to be, quite frankly. Yeah, we have a similar routine for so vertical stretch. I don't really know how to, I mean, this is kind of like duplicated code, but this is going to be the largest horizontal stretch. How are we doing on time? Yeah, a little more than 20 minutes. Okay. And this is similar, so process each row. So now we go. So these basically become inverted. And we can just set the key to 0, 0. And we can say row. This is pretty much the same routine, but with rows and columns swapped. Okay. Column, let's go to the N. Right column. I actually think there's probably a way to. There actually probably is a way we can modify this so we can just write one function and not duplicate the code across. But I think for now we'll keep it as it is. Yeah, I think it's this simple, and then we can say horizontal stretch, vertical stretch. Excuse me. Actually, we can do vertical. We can do actually sort of stretch vowels. We don't need 2 of these. Save a little bit of memory. So stretch vowels instead of vertical stretch, and then we would say int temp, we'll call it, or just t, equals the current stretch vowels. Actually, in this case, we don't even need to do it this way. We can say we can calculate final answer as well. Largest cross starts off at 0. We can actually say t, and then there's stretch. We can say largest cross equals standard min of stretch and t, and it's going to be the standard max of largest cross and this value. Right? can say return, it's going to be largest cross -1, bit shift to the right 1 plus 1. Something like this. I think this is actually all you need. I think you're done. Cannot assign return value because function contains a const value. Sorry, what? Oh, this is not a const. That's my mistake. Forgot about that. Wrong. Oh, no kidding. Whoa, really? What do we get for this largest cross, I guess? No, it's more than possible that I made some error. I might take some time to debug this here. How are we doing? 46 minutes? Alright. Output 1 expected 2. We said... So we got 5. Wait, what? Is this the first example? 5, 4, 2, output 2. This is 3. Well, first things first, 5 is wrong. What? Because this will give you 4. Bit shift 1 is 2. So this actually should give you 3, not... Maybe that's why. But this is supposed to be 5. Okay, there we go. But still wrong. So the 2 is, it's k minus 1, so 5 is definitely wrong, though. 5 is just wrong. So what is the... So this is incorrect. All right, let's see. What did we do wrong? This stretch shouldn't be 5. That's definitely incorrect. How is that 5? Was it 1, 2, 3, 4, 5? This one's 4, 5, 5. Okay, actually, yeah, this is fine. This one, at some point there should be 4 in here, though. Yeah, there's some 4s in there. Okay, that's good. Okay, no, that's fine. That's okay. And then we got our stretch values. The maximum, which is, this is 0, and the minimum of stretch in t. So at each point, there's this stretch amount, which we would say, okay, so this is now row by row, or yeah, row by row, we take each column. So this is first column by column, and now we go row by row. And oh, that's so confusing. This first one is all the rows for each column, So iterating down the rows on each column. And the second one is for each row, there's a column. Yeah, okay. Each row. This is so confusing. I'm sorry, I'm trying to like wrap my brain around it. So there's each column. We go iterate row from the top, row by row, right? But now, now we're going to go each column. We iterate each row. We iterate column by we iterate through the column. We iterate through the row. Okay, that's so confusing. I get so confused. I think about that, but yeah, for each row, we iterate through the columns for that row. Right. And what we're saying here is that we should see. So at this point, we see 5. Oh, there's something wrong here though. Okay, I see the issue. So even though that stretch is all the way, so this isn't 5 on each of these. It's actually wrong. It should be. We should actually write as we. Okay, I did this wrong. I had the wrong idea. That's why it's coming out wrong. So it's actually going to be this stretch. It's going to write to each point. I guess it would be, you write the value that you're at so far, you would write, that's how many you can stretch upwards. But not how many you can, not necessarily how many you can stretch downwards. And actually, it's got to be, the crosses are in the middle. So really, the first value, there's nothing upwards, so it's got to be 0. So actually, you need to see how far you can go down before you can see how far you can go up. So actually, when you write, it's going to be from the top. It's going to be, there's going to be an increasing value. So actually, that's really confusing. But there's going to be the right column x, and then there's going to be another value. We'll call it. So that's very confusing. All right, so there's the right row x, and then we're going to call this like previous, or yeah, previous space stretch is going to be equal to 0, and we're going to increment both of these. We'll call this like top or above, let's say, or previous direction. Yeah, so it's actually with the value represents total amount maximum number of cells in both upwards and downwards directions. Something like this. Values in the given cell, and actually the given column with a value that represents the maximum number of cells in both the upwards and downwards directions before line or a boundary is reached. Yeah, so this is like a very slight, subtle thing, but we're going to have previous to start off at 0, and so we actually, it's not going to be the stretch, it's going to be the minimum of previous and not stretch. It's actually, believe it or not, we're going to be decrementing stretch. So from the right row, we can go, stretch can go all the way down to the bottom. We're going to actually decrement stretch as we go. Yeah. And I think it's okay if stretch becomes negative at some points. I'm just thinking if like it matters whether or not if we have 0 or -1 or something, I think it's fine. So what will happen is the previous is 0, right, above where we're at, and stretch is, this is going to tell us, stretch will tell us, so actually you really should start off at 1, I think. Yeah, so you always include itself. So previous starts off at 1. Stretch is whatever it is. Take the minimum of these two. So the first cell gets a 1. The second cell, you can go up 2 now, itself, plus 1, the previous. And stretch is actually decremented now. So we include this, but we don't include the upwards cell. So stretch has been decremented. So now you take the minimum of those two. And then as you progress, previous gets larger while stretch gets smaller, and you take the minimum of these two values. And that gives you the largest vertical portion of your cross that you can have. And this is really what we need to use to update here, this logic. Values, update our final result value by considering largest horizontal bar or cross. It's not really a cross, but it's, yeah, largest, that can be fixed, largest horizontal bar, and be centered, given cell. And using that value, using that value, largest cross, total cross, that can be found, given cell. Once that value is found, use it to compute the largest cross can be found in the given cell. From there, we can update our desired value result. Okay. These things are really subtle, but we just, for right column, we're going to add previous equals 1, x less than column, plus plus previous. We're going to add this stretch portion. So we're going to say T is stretch values so far. We're going to say stretch values of, we're not going to update this, we're going to say int horizontal bar is going to be the minimum of previous and stretch, and the largest cross is going to be yeah, stretch previous, another bar, cross, standard min of t and horizontal bar. And then finally the largest cross. Take the maximum of this cross. Okay. Something like this is more what we're after. Hopefully that makes sense. Still incorrect. Okay, but this is a little bit better, I think. What do we get at each point here? We can print this value. Could also print row. Okay. And this will just be V, we'll call it. So these are the values we get for our vertical also a little confused. Why is it just row 5 every time? Oh, I guess because each time it reaches the end here. I guess that makes sense. What about this one? That's kind of interesting. But yeah, so we can maybe look at that in a moment. What happens with this mine? But column 0, V1. Actually, no, it's just saying 5 every time. That column 0. That's actually really confusing. What's going on there? Oh no, I think I get it. Okay, no, I get it. That makes sense. That makes sense. It really should be X. This is what we should print. That's super confusing. All right. This should be 0 also in this one. So we got 1, 2, 3, 4, 5. Row 0, 1, 2, 3, 4. So row 4 and columns 0, 1, 2. Column 2. Ah. Okay, it doesn't get ridden. Yeah, that's kind of what I was hoping for. It doesn't get ridden at all. It just stays at 0, which is good. Okay, so these values 1, 2, 3, 2, 1. Right, that's what we expect. And then 1, 2, 3, 2, 1. We should see again. This should be just 1, 1, 2. How's it go? It's column 2 should be 1, 2, and then here it's 2 here, and then this should be 2 again because this is 2, and this is 1. Perfect. And then column 3 should be 1, 1, 2. This one is 3. So what's interesting is 1. I think I'm doing this wrong. also because, excuse me, I guess what we're doing incorrectly is we're saying the stretch in both directions that we can go is 3, but from the initial point, if it's just one cell, it'll be 1. So that's kind of confusing. It's how many cells you can go in either direction, including the initial cell. Yeah. So then that's correct, and then here basically do the same thing, but now horizontally. And what's going to happen is the cross is going to have the furthest direction we can go in all 4 directions, but also including the middle point. So if we can go 3 in all directions, including the middle point, that really actually is 3 here, 3 here, 3 here, and 3 here. So, like let's say we get 3, it's actually, I think it's actually this. So this is what we'd want to return then. I think that's actually what we return. Also, wow, used a lot of time. Okay, over an hour here. Right, if it's just 1, I think it would return a 1. If it's 2, yeah, I think it's actually, this is the right amount we're gonna return. Okay. Let's try some of these test cases. So generating these test cases would be a little more challenging, I think. We can programmatically generate some test cases though. But we want gen test cases. We can do, we would need like a format for our test cases, wouldn't we? We could do 2D test cases. Let's do that. Let's do 2D test cases. Really, we probably want like a master program for our testing, right? We probably want like some program we can like, sort of select different parameters for our test case generation instead of programming each case. So here we're gonna have low bound, high bound, max numbers. We're gonna do, I guess we could do, well, I think for now what we're gonna do is just generate 2 numbers instead of 1. It's gonna be exactly the same thing, but just 2 numbers. So we'll do, it's gonna be this character with a space, and is that typically how I do it? Yeah, usually, no, that's fine. This character, then this character, a space, tdgen the next one, and then a closing bracket, and then a space and a closing bracket, and then right, I think it's the same kind of deal. Let's see. Okay. Oh, I see. Okay. Does it compile? It does. All right. What do we say? We wanted like There's the high bound, low bound, which is I think 0, 500. The values are going to be between 0 and 500, and then the number of test cases will do 10. And first we'll print those, and then we'll put them to TT and Notepad TT. All right, how about this? What happens if we do this? Oh, we need each of these test cases. We need a number as well. Oh no. This is like what you might do with scripts. It's kind of funny. We're gonna call this custom. Yeah, we'll copy gen 2D test cases. We'll just say gen 2D test cases. And we'll just say, I don't know, v1 or something, I don't know, special, I don't know what to call it. Oh boy. This is kind of why I think you probably want like something a little more general than this to do your testing. This is funny though. Let's see. So we can do something like, I just want to programmatically generate my tests. We do something like, we have our low bound, high bound for our numbers, which is randomly generated. And then, so these numbers will all be in this particular range. Oh, there could be duplicates here too. That's a tricky thing. N is going to be our mines. We're going to say C out. I guess for now let's just say 100, but actually it shouldn't be 100. It should actually be high bound, I think. Something like this. Say 2D special. And what did we say? 0 to 500, 500, 10 times to T. Alright. Something like this. I don't know. This may or may not be correct. They might get invalid test cases for this or something. Yeah. 1 to 156 only. I guess the first test case is the one it's failing on. Could do high bound +1, or yeah. Yeah, let's do that. So let's actually remove these test cases. Also, this should be unique, the mines, but that's okay. I think it works. It works okay in either case. This is actually high bound +1. I think it's right. Yeah. Yeah. That makes sense. Okay. And then our routine is actually going to be 499, I believe, is our, so I guess both of these need to be 499. The numbers themselves can be, n could be between 1 and 500, but I think it means, yeah, I think that's actually correct. Alright, what happens when we do this? Programmatically generate our test cases so we can really test this thing before we can submit it. No. It has to be unique also. Okay. The dude does have to be unique. Alright. Sure. Oh boy. Okay. Let's say ensure unique values. Set, or just, yeah, we'll call it set, or S, or check. I don't know. Yeah, we'll just call it set. Ensure unique values. The test case. Not just a hash set, but a Onward set. So we're going to use a custom hash again. We're going to say struct custom hash standard. We're going to say unordered set of standard. We can use vector. We can also use like tuple. Custom hash. And we'll say set. And then we're going to say, so it's kind of interesting, it's standard size, oops, size t. I don't think you need to use standard size t, by the way. I think you just use size t and it works out okay. In our instance, we used, yes, standard size t. I think it's fine. Standard size t. Operator. Const no accept. And what we take is exactly what we're looking at, which is standard tuple of ints on reference x. I think it's actually a and b, right? Or no, yeah, just x, I think. And we're going to use standard hash of int. Call that, excuse me. So standard size t h1. Call this function on x dot first, or really be standard get 0 of x. And then we say get 1 h2, and then return, it's going to be h1 or h1 h2 bit shift to the left 1. You could bit shift to the right 1 as well if you wanted to. So we have our custom hash, and now take that set and we say ensure that we've generated a unique pair of values. So we'll say while, so we'll do this, say key, say tuple int key is equal to standard make tuple of tdgen and while set dot count of key, we're going to reset the key, something else. Alright, keep updating our key, and then we're going to take this to be standard get 0 of our key, and this is standard get 1 of our key. While the set contains, we're gonna add that key. Insert key. Yeah, something like this. Or add, insert, yeah. Let's try to compile that. See what happens. Oh, nice, compiled. No kidding. Uh-oh. Uh-oh. Not quite. So this should be 0, and then we'll insert the key. I'm a little confused by this. I guess it is technically possible to call it to get into an infinite loop here. I guess if these if the only values you can generate are already contained in the set, then you'd have to exit there as well. I can also say int failsafe. I'll just say failsafe is less than 1,000, and increase this failsafe each time. Can't generate anymore. Gracefully setting this loop as well. We should maybe make that a constant, this failsafe constant. So if we reach 1,000, we would want to, also this is taking a lot of time. We're an hour and a half here. I need to go to bed. If we have failsafe at 1,000, then we're going to want to set I equal to nums minus 1. Yeah. Excuse me. Okay. All right. How did we do? It's my randomized test case generator. Does it work? That's the question. That's the question. Did it work? Does it work? Hey, oh, okay, nice. I can be pretty confident with that. Fairly confident with that. May have possibly missed some edge cases. Oh no! You're kidding. Really? We TLE? Oh brother. What? Oh man, I was not expecting that. Really? Whoa. No kidding. Wait, what? No, there's no way. Uh-oh. Whoops. It must be the test case. Wait, what? I think we hit an infinite loop on some test case. Whoa. Uh-oh. Oh. Whoa. What? No way. Hold on, what? What's the test cases passed, but it took too long. What? How's that even possible? I'm so confused. Alright, let's do 56 test cases. They all passed, but they took too long. How's that even possible? I'm so confused. Oh, do we not? Oh. Also, this is apparently not correct as well, which I'm a little bit confused about. I'm a bit confused about this. Oh no. I thought I fixed that already. Oops. I thought we ensured that these are different. Oh. actually. Oh, I see. Okay, so apparently this failsafe was hit a few times. It was hit before, so what can happen? So we want this to only occur okay. So the issue is this failsafe occurs and we exit. We don't add this pair. That's the deal. If we don't hit the failsafe, then we can add the pair. I think that's part of the problem. Let's see if it compiles. Don't mind me just pushing 56 test cases to my test program. No. Not a value of type integer. Oh, that's very awkward. Because now the problem you end up with is oh no, I thought that might be the case. Now the problem you end up with is we can print this after out. We can do it a different way. We can do a different way. This is kind of what I was thinking before. There's a better approach. We can say we'll do it this way. So we'll say generate pairs for set, and then we can just say print so we can just move the I'll explain this shortly. The output, the printing that we're going to do, can just move that to basically move the printing code to the bottom here. And we don't need the rest of this as well, so we can actually take this, move it down here. What do we want else? Don't need any of these things. All right. Generating the pairs for our set. So I less than num. So we hit the failsafe, then we're done. We don't need this part here anymore. Print each pair in the set to the output. Right, so that's the next part. We would say for const auto p in our set, which is, that's kind of interesting also, but yeah, it works, I guess. Set. So what's interesting is the last element that we print. We could do something like this. So int I equals 0, or x equals 0, increment x, and we just say if x is equal to set.size minus 1 is the last thing that we print, then we have this code here where we don't, so as long as we're not equal to the last, or as long as we're less than that, then we can say add this comma and a space, and then we could take our it's a tuple, right? So we can actually use probably could even go ahead and use this notation. I think that works. You know what we're gonna do? We're not gonna do that though. Do a couple things here. We are actually going to use, we're going to do it this way, key, or, yeah, key, auto reference key, do it that way. Yeah, we'll do it this way. Whoops. And we increment x each time, so that way, yeah, so we can, this I think is better. There are a few things to say about this. Let's see if it compiles. Let's start with that. It might not compile. Oh, it did. Okay. Okay. Oh, whoa. Whoa. All right. Got loads of test cases now. See what happens. Wow, can't believe we TLE'd. Struggling to, oh no. One of the test cases is wrong after all that. Of course. I think, really, why? Hmm. 0 and 203 it says. What? What happened? The mines need to be between 0 and 203. And somehow they weren't? very confused. Oh, that's why. Duh. I see the issue. I see. Each test case needs to get its own set. I see the problem. Custom hash doesn't need to be the same. I mean, the custom hash could be the same, but the I see. You see the issue. I see the problem. That's subtle. No, not subtle, but that's not that subtle. That's just, I'm kind of moving quickly, so it's kind of easy to miss that. That's also why it was so big before. Why there were so many. Yeah, that's why it was, the test cases were enormous. It's because there was just way too much being printed. TLE. You're kidding, really? What? Is this a joke? Is this some kind of a joke? Brother, how does that happen? I guess my question is, are we like, which test cases is it TLEing on? Are there specific test cases? Let's just get rid of some of these test cases. Actually, let's do it this way. Let's just generate a bunch. Well, okay. My question is this. Is this TLE because, it shouldn't TLE because we're O of n squared, right? So we just shouldn't be TLEing. So I'm wondering if actually it's not the TLE, but it's actually an infinite loop that we found ourselves in, which I don't think is possible, but it could happen, I guess, in theory. There are quite a few loops inside here, so it's possible. One issue could also be that, excuse me, like, we're sort of going back and forth here when we use these for loops. We're kind of going over everything a second time, which could be part of the problem as well. But I don't think that's the issue. That shouldn't be the problem. That really shouldn't be the issue. Yeah, that really shouldn't be a problem or the problem. Let's try to get rid of some of these, see if we can get it to stop TLEing. I think it's an infinite loop that we're running into. I think it's actually just an infinite loop. Infinite loop. Okay. Yeah, so let's go back, alright, so let's say let's go here. I want to try to cause a problem. I think one of these test cases is causing an infinite loop to happen, and that's why we're getting TLE'd. Okay. So let's say, let's grab a few here. It's got to be one of these test cases. Somehow we're running into a TLE, or somehow I think it's an infinite loop. Could be wrong though. Maybe it's not. So I got like half of them here. Okay. So if we get rid of all of these and just work on this lower half, if this doesn't TLE, then that means it's not an infinite loop and we're just slow in our code, which would be frustrating because then we have to, okay. Great. It just means it's slow. Okay. Alright. Great. How do we make this faster then? We can use these, remove these min functions, that might be why. Could be related. Excuse me. Yeah. Get rid of that one. Same thing, horizontal bar equals previous if horizontal bar is less than, is greater than, or stretch is less than horizontal bar. Update that horizontal bar with stretch. Kind of dislike writing code this way, but this needs to be a little bit faster here. And then finally, we could say largest cross. If we'd say if largest cross is less than cross. Okay. Oh, how are we doing? TLE. Okay. That's not good. I don't know, man. Yeah. What? No. Why is it so slow? No. Brother. All right. How much can we shave off to get this to work? Is it the hash function? Is that it? Okay. I don't know how many test cases. Let's try it. Let's just see how we do. It might be fast enough. I don't think so, but it could be. Brother. What a struggle. What a struggle. I guess my question is it like the total sum that a TLE's on, or is it just TLE on one thing at a time? It even looks like, yeah, that's fine. I think it's just gonna like randomly tealy or not tealy. I think it's really close. I think that's why it's giving me that. Oh no, brother. Got a lot of upvotes. I don't know, man. This seems like it should be fast enough. I don't know why it's not. I think it's because I'm using an unordered set. That's my thinking. Oh, okay. Not sure if this affects anything if I import the library first. Actually, that could have something to do with it. I don't think so, but technically could be relevant. If you just didn't import the library at the top, that would be really annoying. That'd be ridiculous. No, that's not why. How about ordered set? Just a set. How about this? My algorithm is too slow. I think also these vector objects might just be a little slow. That could be something related to. I think the same code should work with the just a regular set. Oh, thank you. Questions, does it, oh, it doesn't TLE, it gives us the wrong answer, but doesn't TLE, so that's really interesting. That's really interesting. Why would that blow my mind? What? What? But now it's the wrong answer? What? Oh, I see. Duh. That's why it's so much faster. That makes sense. That makes sense. Okay, this should TLE. Yeah, okay. Now, if I use tuples instead of, huh. You know what I'm wondering? Maybe we should be processing the mines, not the, maybe I'm doing this wrong. Maybe that's why it's a TLE. Maybe that's why maybe it's a special kind of approach that we're supposed to be taking where we're supposed to be operating on the mines and not on the grid, which I actually think is correct. If you take all of the mines in, and you sort them, and then operate on the mines. Well, you can have 5,000 mines, right? Brother, what's going on? Why is this so hard? N is only 500, so this should at most be performing 500 by 500 operations. we have like a, why is this too slow? This is not that slow. What is going on? No, man, no. Excuse me, this is quadratic time. This really isn't that slow at all. This should be pretty fast. 500 squared is really not bad. Oh, 250,000. Okay, I guess times 56 is kind of a lot. You know what it is? It's we actually are doing like 4 times the work. That must be why. The reason we're doing 4 times the work is because excuse me. 5 times the work is, yeah. The reason we're doing 5 times the work is because it's more than that, but we're dumping the mines here. Why do I feel like 500 times 500? Why do I think that's, okay, I'm just wrong. Yeah, okay, I think I get it. We actually can process just the mines instead of processing on 250,000. We could do, yeah, so we could be like 50 times faster. The way we would process the mines is we could sort the mines, and then each of these stretches we can determine more efficiently by just considering the all of the mines with a certain. We don't even have to sort them. We can actually just dump the mines into like a. Well, actually, yeah, we could dump the mines into a grid. Not really a grid, but more so like, you know, actually I don't even know, some kind of data structure where we can go row by row and column by column and basically perform the same operation, but we iterate over the mines instead of every spot in between. And what would happen is we know, like, we don't actually need to perform these calculations this way. We can do like oh wait, maybe we do. Oh, it's so hard. You could do something like oh, I don't have a solution to this problem, actually. I think maybe you could do something easier where what you can do is at each position you can in constant time find out where in each direction in all 4 directions where the nearest mine is in those directions, or the nearest boundary or mine, and then your cross at that point is going to be the really it's going to be the minimum of each of those directions, of all 4 of those. You could do it that way, I think. That would give you... That would be a much more efficient way to do this. That'd be a lot faster than what we have. I think you do need to visit every row column though, anyway. Yeah, the tricky thing though is what kind of data structure can we use to put our mines in, or we can quickly figure out in each direction which one's the closest. I guess I'll make this part 1 and go to sleep, because this isn't fast enough. This is what was not what I was expecting. Interesting. Kind of a data structure can we use? I don't want to do this in logarithmic time. I guess you could technically do this in logarithmic time, in all 4 directions, but that seems kind of bad. Kind of really want that in constant time. The thing that's really obnoxious about this is that this technically is sort of constant in all 4 directions. It's just you have you're just doing like double the work here in these loops, these inner loops. That's really it. That's pretty much the only difference. Excuse me, like this is actually asymptotically quadratic. Just has maybe another constant factor. Yeah, times 4 times the work, so you're doing double the work here and then double the work here again. So just doing 4 times the work that you need to, I guess. I'm wondering if it's because we're using these vectors of integers. I'm wondering if we can replace this with tuples or something. Yeah, I kind of want to try that. See if that makes a difference at all. I feel like maybe it would. Something tells me it would. Something tells me this might be part of the problem. I don't think so, though. I don't know. Maybe I'm wrong about this. I actually don't really need that anymore either. Is this still correct? Is this still correct? Is the question. Still compile? Is it still? Yeah. No. Okay. Inset. Yeah, that would. That might matter. Does it compile? Is it still correct? Does it run efficiently? Okay. Oh. Was that the problem? Really? Oh. Wow. No kidding. Dude. You gotta be kidding me. Is this a joke? Some kind of sick joke? Nope. 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 The truth is that C++ the C++ compiler works a lot better with tuples. That's just the reality. That is just the reality. would not expect that, but that's just some reason that's what it is. Wow, I can't believe it. Spent all that time trying to figure out a faster way to do this whole time. Just needed to use tuples. Of course. Of course. Wow. That was taking a while. Brother. Compile error. Of course. Also don't really need this anymore. Oh, okay. Oh, wait. I did this wrong. Let's try this again. Wow, 2 hours on this problem. No kidding. This is taking a really long time to think. I guess because it has to load all the test cases and then compile the program and run it on the test cases. I guess that's why it's just parsing all the test cases. So is this faster or slower? That's the question. About to find out. We are about to find out. Oh, TLEs. Whoa. So it looks like the hash set is actually slower than a. That's kind of interesting. That a regular set is actually faster. Imagine that. Whoa. I would not have expected that at all. Okay. Oops. So back to what we had before. Wow, we just made it on this problem. I don't really know a better way to do this, faster way to do this. So this one was slower this time around though. I think I'm just making it. No? That's a big difference. So it's just randomly a lot slower, a lot faster. I don't know, the set seems to be faster than the hash set, which is strange. Yeah, seems to be okay. I don't know what to say. For some reason it's faster. But, that's so weird. So yeah, it's better off with just a regular set. Into a set. Yeah, man. This was kind of brutal. This was kind of brutal. Oh, TLE this time now. It's kind of hit or miss whether or not it TLEs. Wow. It's kind of random. Sometimes it's over, sometimes it's under. Huh. Interesting. But it looks like the set is faster than the hash set. I don't know what to say. I think, you know, you just, what do you even do? We got it, but there are a couple of things. I think if you operate on the mines, there's a slightly faster approach where you can at each point you can find out, you know, how close you are to a mine or a barrier. And I guess you could do that in logarithmic time with respect to the mine, the number of mines in that particular row or column. I think you could do that. You could find those mine positions, and it would be, how would you do that though? The tricky thing about that is you could actually create two, you can copy the mine array twice. I think that's the way to do it. Copy the mine array twice, and in one case you have all of the mines on each row sorted, you know, sort of row by row, so you could just search on that particular row. And then also, so column by column really, and then row by row as well. So given a certain row or column, you can search quickly to find either the mine that's before or the mine that's after. Yes, I think that's the way to do it. And then you obviously have the cases where you meet the boundaries. And so then in logarithmic time, you can find all four directions for each row column. And then you can just use take the minimum of those four in each direction. That would be two things. One, that would be a way more efficient code to write, and two, I think it'll be faster. I think it'll be a lot faster because then the logarithm that you're performing at each step is proportional to the number of mines in each row and column, which we know is quite small. It's at most like 100. And so the logarithm is pretty quick. And you also have you're not using any, oh, you were using a little bit of memory. You're using some memory proportional to the number of mines, which is relatively small, 5,000 mines at most. And then also, you're only performing one iteration. Yeah, here we go. So you're only performing one iteration this time around over your whole array. And then instead of performing these logarithmic routines, rather than performing 4 iterations and then each iteration you're performing this also logarithmic routine, but this is also logarithmic over the entire mindset. So yeah, you'll have much smaller constant, I think, to deal with at the end of it. That's my hope anyway. That's my thinking. Could be wrong about that. But yeah. So let me go. Thank you all for watching. I'll I'll talk to you soon. Have a good rest of your day. There's definitely a better way to do this, but this is, I don't know, I'm kind of annoyed. Like, I think my solution was asymptotically okay, but for whatever reason, they wanted something that was, you know, sort of had a better constant in terms of like the speed. I guess it is what it is. So, alright, so let me go. Thanks again for watching. Talk to you soon. Have a good rest of your night. Yeah, I guess I'm probably going to look at the discussion on this problem. Maybe this is like a part 1 kind of deal. Look at this again, see if there's like a better way that I could approach this. I don't know. I mean, again, asymptotically is optimal. It's asymptotically optimal. It's just they wanted a better constant. I don't, you know, what are you gonna do? What are you gonna do? All right, yeah. Well, it's maybe actually, I could be wrong. It may not be asymptotically optimal. It's technically it is asymptotically optimal. The one with the hash set was optimal, but the runtime was too slow. And then, yeah. Anyway, I'm gonna go. Thank you for watching. Talk to you soon. Have a good rest of your night. I guess that's it.